So magnets, we're talking about one of the fundamental forces of nature. We talked about gravity so far in Physics 1. We've talked about the electric force in the middle part of this semester. Now we're going to talk about a third force, which is very closely aligned with the electric force, and that's the magnetic force. What's important to understand is, unlike the electric force where we can have positive and negative charges, the magnetic dipole, electric dipole, of course, is a positive and negative charge. The magnetic dipole, which has north and south, cannot have the poles separate. So basically, there exists no magnetic monopoles. It's either a magnetic dipole, or we can also have higher order collections of north and south, but north can never be separated from south. You can't have one without the other. Of course, some of the same rules apply to the magnetic force as we have with the electric force. Like poles repel, so a south will repel a south pole, a north pole will repel a north pole, and of course opposite poles attract. Looking at the magnets, if we attempt to separate the poles, we actually end up creating more magnets. So for instance, here's a bar magnet. It has a north pole and a south pole. One would think that if we simply cut this magnet in half, we would end up with the north pole now separated from the south pole. But that's not how it works. As we cut it in half, what we're simply doing is creating a new set of north and south poles. The north pole is now connected to the south pole. This north pole is now connected to this south pole. Cut it up again, we get additional poles. Cut it up down the center. Again, we can never separate north and south pole here. So, understanding something about magnetism, we will see later on in the chapter that there are different types of magnetic materials. We call a material that we can magnetize a ferromagnetic material. This is a type of material where it is so easily magnetized that an external magnetic field will leave a permanent magnet when the magnetic field is removed. And again, we have different types of materials. Ferromagnetic materials include iron and some other materials such as cobalt and nickel. Some rare earth metals are also ferromagnetic. We'll talk about paramagnetic materials, those materials that do have some magnetism, but it's very, very weak and it certainly doesn't stay permanent. Also diamagnetism, which is actually the repulsion of magnetic fields. But if we take iron and we have an unmagnetized piece of iron, we can simply magnetize it by placing it in a strong magnetic field. We can actually stroke it against a magnet, and this will also impart a magnetic field on it. So magnetism can be induced using external magnets, and that's one of the different things that we have from the electric force. With the electric force, we actually have to move charge around. Here we can actually induce a magnetic field in some of these materials. Types of magnetic materials, types of ferromagnetic materials, we have our soft magnetic materials. Iron is easily magnetized, it also easily loses its magnetic field. And what this means is that it's very good for use in recording materials such as magnetic tapes, disk drives for storing information. Those are all composed of ferromagnetic materials, or ferrous materials actually, iron materials, usually iron oxide, because it's not reactive. Once it's in the oxide form, it's not going to react with the oxygen in the air or the water in the air. And again, it's a soft magnetic material, so we can use it to store information. Hard magnetic materials, such as cobalt and nickel, these are more difficult to magnetize. They tend to retain their magnetism as a result, and therefore, we'll use them a lot of times in a permanent magnet. Sometimes we actually alloy soft and hard magnetic materials to get sort of an intermediate type of magnetic material, but cobalt magnets and rare earth ion magnets tend to be a hard magnetic material as opposed to the easily magnetized and demagnetized soft magnetic materials. In fact, just simply dropping some of these iron magnets, we can lose their magnetism by drawing the magnetic domains about. Speaking of magnetic domains, if we look at a microscopic model of what's going on, we can see that a typical magnetic material, typical ferromagnetic material, such as iron, has tiny areas which all have the same magnetic field, but they're completely randomized, so the macroscopic field is zero. Again, on a microscopic scale, we can imagine each of these little squares represents sort of a stylized magnetic field. Now here we only allow for 4 different directions, but in the real world we'd have any possible directions. The reason why we can magnetize these types of materials is that when we apply an external magnetic field, those magnetic fields that are in the direction of the applied magnetic field will cause those domains to grow. What will happen here is the magnetic fields of neighboring atoms will switch the magnetic field to that particular domain, allowing this domain to grow. Same thing if we reverse the polarity of the magnetic field. We suddenly apply a south magnetic pole to this magnet, then the north magnetic poles would suddenly shrink in size, and we would grow the south-oriented magnetic domains. So again, all iron is actually magnetic. It's just that on a microscopic scale, these magnetic fields are completely randomized. There's no preferential direction until we apply an external magnetic field and we orient some of these to grow some of the domains in a particular direction. Then the material becomes magnetized. Sources of magnetic fields, basically what we will see is that the motion of the electrons in the atom are really responsible for the magnetic fields of magnetic materials. So what actually takes place here is we have the electrons acting like a loop of current. On the microscopic scale, we can get magnetic fields pretty much the same way. You'll see that a current of wire has a magnetic field that wraps around it. We can use the right-hand rule to demonstrate the direction that this magnetic field wraps around it. Here we have the current going upward, and as you can see right here, we see this counterclockwise wrapping of the magnetic field around that wire of current. Now if we take the wire and now we close it into a loop, we can see that the magnetic field now becomes concentrated at the center of that loop. And that right there, this loop of wire, is pretty much what we use on the read and write head for a magnetic hard drive using a computer. If we use many loops, we call that a solenoid. This is arranged in a cylindrical geometry. Again, moving current creates a magnetic field. Here's the bar magnet. Also has a very similar magnetic field to the solenoid. This is, one of the simplest models that we often use in terms of a magnetic field. The magnetic field lines point out of the North Pole, just like the electric field lines point away from a positive charge, and they point back into the South Pole. And again, this is magnetized material of some sort, some ferromagnetic material that produces permanent magnet. Of course, the Earth is also a magnet, and we'll talk a little bit about the source of its magnetic field. But again, to understand what's going on here, we have to understand that anytime we have moving current, this moving current generates a magnetic field. So the Earth. The Earth has both a geographical pole and also a geomagnetic pole. And the interesting thing is, the geomagnetic pole actually has the reverse polarity of what we call it. So the north geomagnetic pole is actually south in polarity. The geomagnetic south pole is actually north in polarity. And the reason why we designated them this way is because if we have a small compass magnet, the north pole of this compass magnet will point to the magnetic North Pole. It's attracted to the south polarity of that pole. A little bit confusing. And again, one of the simplest ways to model the Earth's magnetic field is to imagine that it behaves very much like a bar magnet. The magnetic field lines are coming out of the north magnetic polarity, which means that they're actually emanating right around Antarctica, and they're reconnecting with the surface of the Earth somewhere just north of the Hudson Bay. Again, that's the southern polarity, northern geographic direction. Looking at this, the magnetic axis is a little bit off from the axis of rotation. It does vary, and right now the Earth's magnetic field is weakening, so this angle of tilt actually does change a little bit with time. It's approximately 11 degrees. But again, the North Pole geographically and magnetically are not exactly the same. So with that in mind, when you're using a compass, you actually have to be aware of this slight difference between what is true north and what is geomagnetic north. As you get close to the poles, it actually becomes more difficult to determine direction because the field lines begin to point downward. And you can actually find where geomagnetic north is, because with a compass needle, it will actually, instead of wanting to point toward a particular direction, north, south, east, west, it's actually going to want to point downward. And we call this the dip angle of the magnetic field. All right, so once again, the geomagnetic North Pole is somewhere just north of Hudson Bay. This is in Canada. This is up in the very cold tundra, but it's still not all that close to the geographic North Pole. And again, you can find this because at this particular location, at geomagnetic north, the dip angle of a magnet will actually be 90 degrees, which will mean they'll be pointing straight up and down. Here's the Earth's magnetic field superimposed on a map, and we can see that the magnetic north and south is not exactly lined up with the geographical north and south. And taking a look at this, depending on where you are located, that angle between what is true north and what is magnetic north can actually be quite extreme. Right in the middle of the country, it actually does pretty well. But as you go further and further east, there's a larger and larger difference between the angle of your compass reading and the angle of geographic north. Of course, not many people use a compass anymore with GPS, but you can actually see some interesting things where the magnetic field lines actually deviate more than just the geometrical deviation, but deviate due to the local rock structure, which can be magnetized too. Sources of the Earth's magnetic field, what we said before, is we need current, we need electrical current moving to generate a magnetic field. So if we look inside the Earth's interior and we measure the heat coming out of the Earth, we know that the Earth's interior is just much too hot to actually have a permanent magnetism. There's something called the Curie temperature. Above the Curie temperature, nothing can remain ferromagnetic. So if the Earth were simply just a huge iron magnet, it would have to be much cooler on its interior than it is. And we know that the interior of the Earth is actually as hot in some places as the surface of the sun. So instead, we need something more similar to an electromagnet. We need moving current. And the sources of these currents are actually quite complicated, but it has to do with the fact that the core of the Earth rotates at a slightly different speed than the rest of the Earth. And what this does is the inner core is solid, the outer core is molten iron, it sets up these eddy currents, or these eddies within the outer core. And through a somewhat complicated process, we actually induce currents, and these currents in turn generate a magnetic field. So this magnetic field, again, is pretty much being generated within the liquid outer core of the Earth. And what's interesting is it changes polarity ever so often. Again, if this were a completely solid magnet, that would be a completely unexpected result. But both the Earth and the Sun have these magnetic dynamos within them, which generate the magnetic field, and because of this, they'll actually switch polarities. Now, the mean time, the average time that it takes to switch is about roughly 1/4 of a million years. However, the last reversal, showing you how non-periodic this was roughly 790,000 years ago. It is in the process right now of reversing. However, this can take hundreds or even thousands of years to occur. So we're going through quite a long period of one magnetic polarity. But again, you can see very clearly, and this has been recorded in rock, any rock that contains iron will actually record the magnetic field at the time that this rock was cool. So basalt, for instance, has a large iron content in it. We look at the magnetic orientation, the magnetic polarity of basalt rock, especially on the ocean floor. We can see that it switches polarity every so often. And again, these are millions of years. So you can see sometimes the switch happens very rapidly. Sometimes it takes much longer to switch. Here's our current magnetic state right here, but you can see smaller and larger regions. White representing a reverse polarity, black representing the current polarity.